Welcome to lecture 3 on module 8. In the module 8, we are discussing on evaporation. Now, today's lecture, this is the last lecture on evaporation chapter. We are going to discuss the calculation procedures and we will demonstrate with some problems. So, this is basically this lecture is on evaporation or evaporator calculations. Now, in the evaporator calculations, we will be discussing two things. We will first start with a we will see first a single effect calculation, and then we will go for multi effect or multiple effect calculation. Now, one thing is pretty clear that when you have to go for evaporation calculation or evaporator calculations, basically our target is to find out that or the design of the evaporator, our target is to find out the area of heat exchange, that is the most important thing. And while doing this, that we have to see that while going for this calculation, we have to see that we are taking the mass balance and energy balance, that these are the two important issues that has to be taken into considerations. That is, one is called mass balance and other one is the energy balance. So, these are the two things we have to do, and all the things calculations will be showing in terms of steady state process. Okay. So, now if we just start with the single effect calculation. It is like this. Say, let us draw a simple single effect evaporator. It is like this, and here. So, this is the part of these things, the evaporator tubes kind of things. So, this is the feed here, and here it is the steam. So, feed this say m dot is the flow rate, mass flow rate, and the suffix indicates that kind of stream it is. So, F indicates the feed and m dot, m is the mass, dot means m dot is the mass flow rate, and Hf is the enthalpy of this feed stream. Similarly, m dot s is the mass flow rate of the steam, and Hs, small hs is the enthalpy of the steam that is entering into, and then there will be a condensate. Okay. And this condensate, say if I say that m dot s again will be the, because the same mass whatever steam is entering, that is getting condensed. So, our consideration over is the saturated steam. So, heating medium is that condensing steam is nothing but the heating medium. So, only the latent heat is involved. In this case, there is no extra loss. So, there is no mass loss even. So, m dot s that is entering and that m dot s is coming here, and in our calculation we will see that no other energy loss of energy is neglected. So, these are the assumptions, and m dot s is this steam again, and then say in the condensate we will have say H L is the latent heat, and then we will have a product here, that is the product, and we can have a vapor here. So, this is the vapor, it is also a product, and this is also a product. This is the thick liquor is the main product, and this is the vapor. We will write it to be vapor m dot V, and H V is the latent heat, and here m dot P is the product flow rate, and H P is the latent heat. In that case, so from simple mass balance, we will get that m dot F is equal to m dot, that is the feed that is entering in. So, mass balance of solution, that is what is to be done. For mass balance of the steam is not necessary, because we have assumed that whatever steam is entering, that is getting condensed. So, that part is not important for us. What is important is that the energy transport from the steam part to the fluid part is important. So, m dot F is equal to m dot say V plus m dot P, that is the product, and then energy balance says that m dot f h f, this is a simple one, plus m dot s h s is equal to m dot p h p plus m dot v h v plus m dot s h l. This is the leak condensate which is coming with an enthalpy. So, now if these two combines, then it will give you the latent heat of condensation. So, we are writing at m dot f h f plus m dot s into h l h h minus h s. This is h s. H s minus h l will be the lambda. So, m dot into lambda s, that is the latent heat of condensation of the steam, and that will be equal to m dot p h p plus m dot v h v. So, this is the general mass balance equation that we can get, and once we know, and also once we know that, so how much amount of the heat transport, this is nothing but the heat that is getting transported, and if we assume that there is no heat loss, then we can find out that q dot is the rate of heat transfer that is equal to m dot into lambda s, m dot s into lambda s, that will be the rate of heat transfer, and if delta T is the driving force for heat transfer, and that will be, this should be nothing but the T s minus T b, where this T s is saturation temperature of steam in cell, and T b is nothing but the boiling point of the solution at the pressure of the vapor chamber. Okay. So, therefore, this is becoming that driving force, and then we can say that q dot is equal to u d is the overall heat transfer coefficient into area into delta T. So, from this relationship, if u d is known, then A can be calculated. So, this is the bottom line for this case, and this driving force, this driving force includes the boiling point, or rather BPE, boiling point elevation, we have discussed in the last class. Actually, the boiling point could be, so if we see that what is the boiling point elevation in this case, it will be that say T b minus T w, that is nothing but the boiling point elevation. So, this will be the boiling point of the solution, and this is the boiling point of water at that pressure of vapor chamber. Okay. So, this is nothing but the boiling point emission, that elevation that we have already discussed. Fine. So, this is the basic conception. Now, if we take a problem on this, quickly we will see a problem on this, that a single effect evaporator concentrates a 6% sucrose solution at the rate of 24,000 kg per hour. Okay. 6% at the rate of 2, concentration is 48%, using steam at, that is saturated steam at 1.8 atmosphere absolute. Okay, pressure. Now, the feed is at 30 degree centigrade and a vacuum of 640 millimeter mercury okay, is maintained in the evaporator. That means, it is a single effect evaporator and it is under vacuum, and the vacuum is of 640 millimeters. So, absolute pressure is much lower. Okay. Now, the heat transfer coefficient, which is overall, okay, overall heat transfer coefficient is 1800 watt per meter square per degree centigrade. Okay. Then what is the area of the evaporator? So, this is to be calculated. Now, given is that specific heat of feed equals to 3.9 kilojoule per kg per degree centigrade, and specific heat of product equals to 3.15 kilojoule per kg per degree centigrade. As we have seen that with increase in concentration of the product, your solute, the specific heat is decreasing, and boiling point elevation is given as 5 degree centigrade. So, these are the certain data being provided. Now, if we have to go ahead with the solution, so first what we have to do is that absolute pressure in the evaporator is equal to 760 minus 640, that is 120 millimeter mercury. So, it is under as a huge vacuum, and boiling point of water at 120 millimeter. So, this has to be found out from the steam table, is equal to 55 degree centigrade, and boiling point elevation is 5 degree centigrade. So, total, so or rather boiling point of the concentrated solution in the evaporator, okay, and that is equal to 55 plus 5 equal to 60 degree centigrade, fine. And say 0 degree centigrade is taken, I will take as a reference temperature or datum temperature, fine. Then enthalpy of feed, okay, and that is equal to 24,000 is the feed flow rate into 3.9 into 30 minus 0, that is the driving delta T, and that is equal to 2.81 into 10 to the power 6, and that is kilojoule per kg. Similarly, enthalpy of vapor generated. So, to find out the vapor generated, what we have to do? We have to do the mass balance. So, basis, if I do take the basis equal to 1 hour, and then feed equals to 24,000 kg, then sucrose in feed, that is equal to 1, that is how much is given, it is 6%. So, 1440 kg. So, 0.06 into 24,000. Okay. So, concentration, because final concentration is equal to 48%. So, total mass of product is equal to 1440 by 0.48, and that is equal to 3000 kg, that is per hour, because basis is hour. Okay. So, water evaporated, that will be equal to 24,000 minus 3000, this is equal to 21,000 kg, and that is definitely basis is per hour. So, it will be in power hour. Now, we will go for enthalpy of vapor generated. Okay. Now, here this will be 21,000 is the amount of vapor generated, and 4.18, that is the Cp of the vapor, water vapor, into 60. Okay. The temperature difference, actually this is the amount of water that has taken, that is being there, minus 0, okay, plus 2370 into 21,000. This is the latent heat of vaporization. 2370 is that, I should say, latent heat of vaporization, and this this is the this is that enthalpy of specific heat of concentrated solution. Concentrated solution, but this is the specific heat of water, because we are considering the water, heat balance for the water. So, 21,000 of the water. So, what was the specific heat with this kind of water? This is this much, 4.18 into the 21,000 into this. This is the sensibility which was present with water. Okay. That is the enthalpy that was present with water. Okay. And this plus this is the latent heat. So, this gives then it is becoming 5.50 into 10 to the power 7 latent heat of and kilojoule per hour, and this becomes latent heat of vaporization of water at 60 degree centigrade, okay, and in kilojoule per kg. And we can see that this operation is happening at 60 degree centigrade, that the vaporization takes place at 60 degree centigrade. So, this is the latent heat of vaporization. Okay. So, therefore, this is the sensible heat for this or whatever amount of present with respect to 0 degree centigrade, the sensible heat present with the water vapor, with the water, liquid water, and then this is liquid, and then this is the latent heat. So, this two is becoming add up and it's giving it to vaporize. So, enthalpy of vapor generated is this, and then enthalpy of product equals to 3000 into 3.15 is the specific heat into 60 minus 0, that is the driving force. So, this is becoming 5.67 into 10 to the power 5 kilojoule per hour. So, from energy balance or enthalpy balance, okay, then enthalpy of steam is nearly equal to 5.1 into 10 to the power 7 kilojoule per hour. Okay. And then once I know this enthalpy, so at 1.8 bar, so atmosphere pressure, steam temperature, saturated steam temperature is equal to 117 degree centigrade, okay, and heat of condensation equals to 2210 kilojoule per kg. Fine. Then amount of steam supplied would be 5.1 into 10 to the power 7 divided by 2210, and that is equal to 2.31 into 10 to the power 4 kg. So, this is the steam requirement. So, area of heat transfer is equal to Q dot A, that is equal to Q dot by U d into delta T. So, U d is given. So, it is becoming 5.1 into 10 to the power 7, that is the heat transfer by the steam, by 1.8 into 3600, this per unit hour. This is 1800 is the joule. So, I am this is watt per meter per second. So, it is per hour it is made and it is in kilojoule is maintained. So, it is the unit conversion into 117 minus 60. So, this gives as 1838 meter square. So, this is becoming the area of the heat exchanger that is needed for this. So, this is just to give an idea about the heat transfer calculations, okay, heat evaporator calculations. Now, let us come to the multiple effect evaporator calculation. So, what we will do is I will just quickly draw such evaporator sections, 3 such has to be drawn. I am sorry. The idea behind this evaporator, the multiple effect evaporator, the evaporator areas are usually tried to be maintained similar, so that it is easy the size of the, so that it is easy to do the design. So, size of the evaporator is maintained more or less constant. So, this is the feed that is coming m dot f T f, and this is the steam that is coming m dot s T s, and then P s, pressure of the saturated steam, and this is here P 1 is the pressure, T b 1 is the boiling temperature, and this is the vapor that is coming, that is m dot S 1, which is with H S 1, and then it is at a pressure of P 1, and this vapor is coming, and this is coming as a steam fed to this, and bottom product is going to there, and it is coming as a feed over here, and it has got. So, this will be m dot f minus m dot S 1, which is gone as a vapor. This much amount is going there, and it is having say H 1, and T b 1 is the boiling point, true boiling point of the concentrated solution. Similarly, here it will be like this, it will go like this, and here it will be m dot f minus m dot S 1 minus m dot S 2. So, these are actually that this itself takes care of the mass balance, okay. And from here it is coming like this. So, this is the steam that is fed into. So, here it is m dot S 2, that is quite clear, and H S 2 is the latent heat, and it's the P 2 is the pressure here, and here T b 2 is the temperature here, P 3 is the temperature here, and T b 3 is the temperature over here, and here again the condensate the product is coming out, and this product would be m dot f minus m dot S 1 minus m dot S 2 minus it should be m dot S 3, okay, and which is having enthalpy H 3 and say T b 3 is the boiling point. Here also m dot enthalpy will be H 2 and T b 2, and here the vapor is going out, it is now left to atmosphere. This is at say P 3, and it has got enthalpy H S 3 and all this. So, and here in all the cases we will have some condensate, okay. This will be the condensate, this will be the condensate. So, steam is coming, and this is the condensate. So, this is the typical diagram of a triple effect evaporator. So, it is a triple effect forward feed evaporator system. Now, one thing I should say that while mass balance is already taken care of while giving these values, and the boiling point. So, if I say that, so this is the effect 1, this is effect 2, and this is effect 3. Steam is put into the first effect, the saturated steam, external steam, so is effect 1. And we should say that BPE, boiling point elevation in effect 1 equals to Tb 1 minus Tw 1, and Tw 1 is the temperature of saturation, Tw 1 is the boiling point of pure water at P 1 pressure. Okay. Similarly, Tw 2 is boiling point of water at P 2, and Tw 3 is the boiling point of water at pressure P 3. That is when these pressures are maintained in the subsequent evaporators. So, we can say that P3 is less than, P2 is less than P1. So, we know that TW3 is less than, TW2 is less than TW1, and that also should be less than Ts, which is the steam, and this less than say Ps. Ps is the, say, if I say the steam pressure. So, this is Ps. Okay. So, we can say that this is the steam temperature that we know, external steam temperature. Okay. And this is the boiling point elevation. So, if we say boiling point elevation in effect 1 is this, BP in effect 2, that will be equal to TB2 minus TW2, and BPE boiling point elevation in effect 3, it will be equal to TB3 minus TW3, that will be the boiling point elevation, and these are the amount of superheat also. These are amount of, they are also the amount of superheat, and we will assume that when the superheated vapor enters from one effect to the other effect, it immediately loses the superheat, and so therefore, the driving force for effect 1, that will be equal to Ts steam temperature minus TB1 boiling point temperature, and this driving force for effect 2, and that will be equal to the steam temperature. Steam is coming with a temperature of say TW1 minus, and it should be for effect 2 TW1 minus TB2, and for effect 3 will be equal to TW2 minus TB3. Okay. And also we know that TB1 is greater than TB2 is greater than TB3, that already we have discussed. Fine. Now, if we go for the energy balance, mass balance already been taken care of. If we do, and this is done neglecting any energy loss to the surroundings or to the ambient. Okay. Now, for effect 1, we will have m dot f h f plus m dot s h s, that is equal to m dot f minus m dot s 1, okay, and that is h 1 plus m dot s 1 h s 1, that is the vapor, this is the concentrated liquid, this vapor, and this is the m dot s h l 1, this is the condensate. Okay. So, this is feed, this is steam, this is your vapor, sorry, this is the product, this is vapor, and this is condensate. And if we just write for each and every cases, this condensate will be m dot s, h l 1, this will be m dot as this. Okay. So, I am not writing these things again. Fine. Now, like this, if we go ahead, this is becoming this. So, from there we can write as this implies that m dot f in terms of latent heat we write h f plus m dot into lambda s, m dot s lambda s. So, latent heat for this first effect, and that will be equal to m dot f minus m dot s 1 into h 1 plus m dot s 1 into h s 1, this is the for vapor. Okay. So, this is becoming that, and this is the latent heat of condensate, condensation. Okay. Now, comes for effect 2. For effect 2, it is m dot f minus similar way m dot s 1 into h 1 plus m dot s 1 lambda s 1 will be equal to m dot f minus m dot s 1 minus m dot s 2 into h 2 plus m dot s 2 HS2, exactly the similar way that is to be done. And then for effect 3, it will be again that m dot f minus m dot S1 minus m dot S2 into say H1 plus m dot S2 into lambda S2. So, it is another latent heat. So, latent heat of evaporation will change because the temperatures are different for the steams. Okay, latent heat of evaporation or condensation is change different, and that will be equal to m dot F minus m dot S1 minus m dot S2 minus m dot S3, okay, into H3, then plus m dot S3 into HS3. So, this is what is being done. Now, say UD1, UD2 and UD3 are overall heat transfer coefficients. For effects 1, 2 and 3. So, under that situation we can write that Q dot 1 is equal to m dot S lambda S is equal to UD1 A1 Ts minus Tb1, okay, and that is equal to UD1 A1 delta T1, and Q dot 2 is equal to m dot S lambda S1 and that is equal to UD2 A2, and this is equal to Tw1 minus Tb2, and this is equal to UD2 A2 delta T2 and Q dot 3. So, these are the heat transferred m dot S2 lambda S2. So, this is similar, not much complication is there. This will be equal to UD3 A3 into Tw2 minus Tb3, and that is UD3 A3 into delta T3. The question is, in usual situation, as I told previously also that because from design point of view, it is tried to have A1 is equal to A2 is equal to A3 is equal to A. It is tried to have similar areas for this, and then under that situation UD1 delta T1 will be equal to UD2 delta T2 will be equal to UD3 delta T3, and from there we can write that delta T summation of delta T would be equal to delta T1 plus delta T2 plus delta T3, and that is equal to Ts steam pressure steam temperature external steam temperature saturation temperature minus Tw3 minus summation of all the boiling point elevations. This can be proved. If we put the values of this, we can prove it. Okay. And summation of boiling points elevation we have already seen. So, then from there, as delta T is proportional to 1 by UD, we can write we can calculate from this we can calculate that delta T values. So, delta T by summation of delta T, that is equal to 1 by UD1 by 1 by UD1 plus 1 by UD2 plus 1 by UD3, provided in all the cases area constant for or same area is same for all effects. So, now what is being done in this case? This way you can find out the delta T. What is being done in these cases in case of design of the evaporators? First, that all the SSI data are calculated, then some area is assumed to be same for all the effects, and then based on that we have to calculate the values of the temperatures delta T, and once the delta T is known, then we will recalculate the areas. So, by knowing delta T, calculate areas is like this: delta T1 area will be, we know ms lambda s by UD1 delta T1, then area 2 will be equal to ms dot lambda S1 by UD2 delta T2, and area 3 also will be calculating ms2 lambda S2 by UD3 delta T3. So, by this way we can calculate the areas again and see that whether areas are correct or not. If not, then revise delta T values, recalculate areas till A1 is nearly equal to A2 is nearly equal to A3. So, this is the basic motto or basic objective or basic ways of doing the heat exchanger design. Now, if I solve a problem, not heat exchanger, evaporator design. Now, if you solve a problem, problem 2, quickly I will tell, say an aqueous solution of a high molecular weight solute is concentrated from 2% to 30% by weight in a forward feed double effect. So, just in place of having triple effect, we are writing it for a double effect. We are doing the problem for the double effect evaporator. This is just to show the principles how to do this. The feed rate is 5000 kg per hour, feed at 50 degree centigrade enters the first effect, saturated steam at an absolute pressure of 2.0 bar is supplied to the first effect naturally. Okay. The pressure in the second effect is 0. Is quite a low value, 1 bar. So, that almost in vacuum, the overall heat transfer coefficients for 1 and 2 effects are say 1800 and 1400 watt per meter square per Kelvin respectively. Okay. Now, calculate the areas of the effects, fine, and specific heat of the liquid is 4.1 kilojoule per kg per Kelvin. So, now if you see the solution, how to go for the solution, we know that feed rate equals to 5000 kg per hour. In this solid is 5000 into 0.2 and that is equal to 100 kg per hour. So, water in it is equal to 4900 kg per hour, fine. Now, product has got 30% solid. So, mass flow rate m dot product, mass flow rate of product will be equal to 333.33 kg per hour. So, water out is equal to 333.33 minus 100 is the solute. So, 233.33 kg per hour, that is the water out as with product. So, water evaporated, that is equal to m dot S1 plus m dot S2, this is coming from the two effects, total water. So, this is total water evaporated and that will be equal to 4900 minus 233.33 kg per hour and this becoming 4666.67 kg per hour. So, this is say equation 1 and then we will do this, that say boiling temperature in first effect okay. Pressure is equal to 2 bar, okay. Temperature is will be equal to T s is equal to 120 degree centigrade, the steam temperature, saturated steam, and its lambda value would be equal to 2200 kilojoule per kg, that is the lambda value. And then absolute pressure in second effect is equal to 0.0140 bar. So, boiling point will be equal to of water will be 285 Kelvin, and that is 12 degree centigrade, and then lambda S2 will be equal to 2470 kilojoule per kg. Now, boiling point elevation is neglected in this case because high molecular weight solute. Fine. Now, total temperature drop. That means, what I do not know is that pressure of the or the temperature of the fast effect, that is not known. So, temperature of fast effect is not known, that is to be calculated. Boiling temperature. So, this is what is to be calculated. So, what we need to know is the delta T is equal to delta T 1 plus delta T 2 as we have seen, and that will be equal to T s minus T 2, and the boiling point elevation is equal to 0. So, this is happening to be 108 degree centigrade, and then from here delta T 1 by delta T 2, that is also 1400 by 1800, that is based on U d 1 delta T 1 will be equal to U d 2 delta T 2, A 1 is equal to A 2, that is from this relationship. So, we can have delta T 1 by delta T 2, that will be equal to 0.78 or something like that, and then from here we can find out delta T 1 is equal to 47 degree centigrade, and delta T 2 is equal to 61 degree centigrade. 61 degree centigrade. So, we know that then T 1 is becoming boiling temperature will be equal to 73 degree centigrade, and then this gives us that T 2 will be equal to 12 degree centigrade. Already it is matching, whatever is there 12 degree centigrade is matching. Now, for effect 1, if we do the calculations, then m dot f H f plus m dot s lambda s is equal to m dot f minus m dot s 1 into H 1 plus m dot s 1 H s 1, and here we will take the reference temperature is equal to T 1, and that is equal to 73 degree centigrade. And from there, so if this is there, then we can write that this is equal to 5000 into latent heat 4.1 of the feed, Cp of feed is equal to 4.1 into 50 minus 73. So, it is negative quantity plus say m dot s into 2200 will be equal to H 1 is equal to 0, this part is 0, and this part is m dot s 1 into 2330. So, from this we can find out that m dot s 1 will be equal to 0.944 m dot s minus 202. Similarly, for effect 2 we will have say m dot f minus m dot s 1 into H 1 plus m dot s 1 lambda s 1 will be equal to m dot f minus m dot s 1 minus m dot s 2 H 2 plus m dot s 2 H s 2. Here reference temperature will take as T 2 is equal to 12 degree centigrade. 12 degree centigrade. So, then we can write that. So, this is I will say equation 2, we can write as 1.25 5000 minus m dot s 1 into 73 minus 12 into 4.1 plus 2330 m dot s 1, and this part equal to 0 will be equal to 2470 m dot lambda S2 m dot S2 m dot S2. So, we can find out that m dot S2 is equal to 0.842 m dot S1 plus 506. Now, this is equation 3. So, if we solve all the 3 equations, we will get m dot S is equal to S1 is equal to 2407.89 kg per hour, m dot S2 is equal to this is m dot S2, m dot S1 is equal to 2258.78 kg per hour, and m dot S that is equal to 2606.76 kg per hour. So, from there we can find out area 1 is equal to Q 1 by U 1 delta T 1 is equal to m dot S lambda S by U delta T 1, and that is equal to 2606.76 into 2200 by 1800 into 47, and that is giving 67.79 meter square, and A 2 is equal to again Q 2 dot by U 2 delta T 2, and that is equal to m dot S 1 lambda S 1 by U 2, this is U D 1 U D 2 delta T 2, and that is equal to 2258.78 divided by into 2330 where 1400 into 61.63 meter square. Okay. So, actually this should be into 3600 by 1000 to maintain the unit consistency, and this will become then divided by 3.6 meter square, and that is coming to be 18.83 meter square. And similarly, here also it will be divided by 3600 by 1000. This 1000 is to make this into in terms of kilojoule. So, this is divided by 3.6, and then it is becoming 17.11 meter square. So, this way we have got this, they are very close, A1 and A2 are close, A2 are close, but we have to make to be more or less equal. So, for that what we have to do? We have to redo the calculation for refining or improvement. Then delta T 1 will take as say 48 degree centigrade, and delta T 2 will take say 60 degree centigrade, and redo till A 1 is nearly equal to A 2. So, this is the thing that is being done in case of evaporation calculations. Now, last thing what I am going to discuss is that vapor recompression So, what is the idea is that in case of evaporators, what we have seen that multiple effect is being used to increase the economy, because by this way that from the same amount of energy coming from the external steam, some steam is generated from different effects, and so we are getting a good amount of economy. The similar economy can also be found out, can also be done, can also be maintained by putting the evaporator, a single effect evaporator also it can be done, but in that case the vapor which is coming out from the top, which is discarded in case of single effect evaporator, that is to be compressed. That means that is why it is called recompression. So, the vapor from the single effect evaporator can be recompressed, okay, and then circulated back. Recompression is needed because the pressure of the vapor in the evaporator is low than the pressure of the saturated steam which is entering into the evaporator from the external supply. So, therefore, that vapor has to be compressed back and recirculated. and then while compressing, then what it is doing is it is increasing the temperature of the evaporator, it is increasing the temperature of the vapor that is being recirculated back, as well as it is increasing the pressure. So, this is called vapor recompression, and then many a times these vapor recompressions become an alternative issue, where a single effect evaporator with an arrangement of vapor recompression can act as a substitute to multiple effect evaporator. So, therefore, the vapor recompression can be done by two ways. One is called thermal recompression. It is called thermorecompression, and this is called mechanical recompression. So, there are the usual two ways by which it is being done, thermorecompression and mechanical recompression. And in case of thermorecompression, what is being done is that there is a steam jet ejector. Steam jet ejector is there, and in which what is being there is that this ejector is used, steam jet ejector is used to increase the pressure as well as temperature in this case. And here there is a one is called motive fluid, that is high pressure steam, and that low pressure steam. This is called load. These two are mixed to generate steam of intermediate and required pressure and temperature. So, this is being done in case of thermorecompression, the steam ejector and motive fluid. Steam ejector is used, and motive fluid, that is the high pressure steam, and low pressure steam, that is the load. So, this is an external supply and this is the load. This is coming from the single effect evaporator. These two are somehow mixed, and the details can be seen from different places, mixed to generate a steam of intermediate characteristics in the form of pressure and temperature, which is then entering back or recirculated back to the single effect evaporator. But in case of mechanical recompression, what is being done? It is a simply it is the mechanical device is used for compression, and for large steam flow, it is centrifugal compressor is used, and for small steam flow, it is that positive displacement compressor is used. Okay. Now, centrifugal compressor is used for large volume to be handled, and for a small volume to be handled for steam, the positive displacement compressor is used, and the compressor ratio is usually is nearly equal to 2.1, okay, is very common. So, what is meant is that vapor recompression unit associated with a single effect evaporator sometimes work as an alternative to multiple effect evaporator. In this case, that this vapor which is coming is compressed and then recirculated back, and this and again put into the same evaporator. So, this way it can work, and this is sometimes acting as a replacement to multiple effect evaporator in terms of improving economy. And then this vapor compression can be done by two ways, as I discussed. One is called thermo and one is mechanical recompression, and usually the compression ratio which is desirable is 2:1, which is very common. When when an evaporator operates at large driving force, vapor recompression may not be economical. At the same time, when operates at low driving force, large area is needed. So, this is also not desired. So, what is done is to be a trade off. So, a trade off between the two opposing factors need to be considered as considered while deciding on type of evaporator to be used. Okay. So, this is what about this evaporation we have discussed. We have discussed about the basic concepts of evaporation, and then what we have discussed is that different type of evaporators available. Then also we have discussed that calculations procedure for single effect evaporator as well as multiple effect evaporator, and with some problems we have seen that how to calculate this double effect evaporator or a single effect evaporator. We have seen, in addition to this, there is one important aspect of which is very common and very important aspect, which is the vapor recompression. Many a times it is used for practice, is being discussed in brief. So, this is all about this module, and the next module is we are going to discuss on radiation heat transfer. Thank you very much.